I hope I'll assume that you're comfortable with your values, you're comfortable with the process. If anyone wants me to go through how you got what you got, I will. But at this point, you should have verticals for the moon and the sun. Compare your values with these. If you got values in between some of the moon values, your sun values should land between the same pair. So you've got an idea that you did it correctly. And then your hang time, I didn't ask for any of your guys' hang times, but again, this is something you should be familiar with given the kinematic stuff we just did to find your hang time. What was someone's, Henry, you had the largest value here for the hang time on the moon. What would your hang time be? Henry. Did anyone calculate their hang time on the moon? Yeah, Ezra. 3.91 seconds. So you're in the air for almost 4 seconds on the moon. Kai, what did you get?
1.86 seconds.
1.86 seconds. So your hang time is about 2 seconds. Jaden, did you get a hang time? Brad?
1.51 seconds.
1 point. Yeah. Time on the moon. Up and back down. So you found it.
3.02.
Okay, yeah. So you guys need to make sure when you're finding hang time, it's not just the time to the top. It's up and back down. So you need to double it. So all of you should be in the 2 to 4 second range. And that's an uncomfortably long time. I don't know if you guys have, if you stop to think about, how long that time actually is, that would mean starting here. You said 3.9, Ezra? Okay. So that means you jump, and you're in the air, and you're back down. That's a long time to be floating through the air on the moon. I don't know, 3 seconds or 4 seconds doesn't sound like a lot, but it's an uncomfortable length of time. So here talking about gravity, here's a bit of an aside. Perhaps you've talked about this before. Again, it depends on what your interests are. Those who are into aviation, these values come here, or into racing. In extreme situations, these terms kind of get thrown around. So the idea of G-forces. Hands up if you've ever heard the term G-force. Okay. So a G-force is a measurement of acceleration, which we don't typically think of it that way. We just kind of think of it as a pressure, but it's not. A G-force is a measurement of an acceleration experienced by an object related to the value we have for the acceleration due to gravity. So as you fall, you're walking down the hallway and someone trips you. You're falling towards the ground at 1 G. That is just standard Earth gravity. Typically, though, when we talk about racing or we talk about flying in a plane or even on a roller coaster, we talk about G's. It's always a measure of a multiplier of this value right here. So if a car is accelerating at 4.9 meters per second, 4.9 divided by 9.8 is 0.5. So 4.9 meters per second squared is half a G. Conversely, the space shuttle doesn't exist anymore, which is really sad. But during liftoff, the space shuttle accelerated at 28 meters per second squared straight up, which is pretty impressive. That value is kind of ridiculous. How many G's is that? Well, how many times greater is 28 than 9.8? So you take your acceleration, you divide it by 9.8, and you're going to get how many G's this would be. This is 2.86 G's. So it's all based on the idea of G-forces is all based on what is your multiplier compared to the acceleration due to gravity. You guys, normal people, typically can withstand about 4 G's. With no training, with no special equipment, your average human being can withstand 4 G's. What that means is past 4 G's is where you start to lose consciousness. You train, you get special equipment. Now all of a sudden you can be taught how to withstand greater Gs. So a fighter pilot can withstand about 9 Gs, given their equipment, given how they condition their bodies, they can maintain consciousness up to about 9 Gs. The aircraft around them generally is designed for about 11 Gs, at which point the airframe itself starts to deteriorate. Like an F-16, for example, one of the more extreme examples of a fighter aircraft, past 11 Gs, the aircraft is no longer airworthy. The fractures start to happen on the aircraft, for example. So you get these multipliers of this value here, and that's really what G forces are. It has nothing to do with force. It has everything to do with the acceleration due to gravity. Comments, questions, concerns? Okay, so then this last piece here, what acceleration would cause each to pass out? If you have 4 Gs, if you want to go the other way now, what is 4 Gs as an acceleration? Well, you take your value for the amount of Gs and you multiply it by the value of 1 G. So 4 times 9.8 is 39.2 meters per second squared. Meters per second squared. And you get, looking for an example of what could do this. No, I can't find one. Okay. Oh, shoot. I was looking for an example. I can't find one. So this is what is meant by G-forces. Comments, questions, concerns? Okay. One of the easiest ways to get accelerations like this, if you remember what it means to accelerate, an acceleration is to change in velocity. So you can change your velocity by speeding up, slowing down, or by turning a corner. And that's it's the turning a corner is the easiest way to experience these kinds of accelerations. And if you take Physics 12 with Mr. Morrison next year, you'll look at how turning these kinds of corners creates these kinds of Gs. You'll do a whole unit on what's called uniform circular motion, which is it's effectively all you're doing is cornering. Okay, flip the page. Let's do today's lesson. So we did Newton's first law. We talked about inertia. Let's take a look at Newton's second law. We're going to jump kind of back and forth between Newton's laws and examples of forces. So Newton's first law, every object will, I'll just quote it directly. Where was it? Newton's first law, every object in motion will stay in motion, and an object at rest will stay at rest unless acted upon by an unbalanced force. Does anyone know the second law? Again, you've probably heard it at some point over the course of your life. The first one is the motion law, inertia. Does anyone know the second? Or I want to take a guess at what the second is. The second one is actually the most useful. Newton's second law is something we've danced around a little bit here already. It's the idea that a net force, and if you remember what a net force is from last week, a net force means an unbalanced force, a net force will produce an acceleration. So if you have forces that are acting on an object, that are unbalanced. Hello. What's up? Good, man. How are you? What's up? Okay. Relearn some physics. Okay. So if you've got an unbalanced force, the object you have the unbalanced force on will start to accelerate. The formula looks very similar to a formula we've got already. Yesterday I gave you a formula for gravity. We said that Fg, or the force of gravity, is equal to the mass of the object times g, the gravitational field strength. But g was also an acceleration due to gravity. If we generalize that formula, instead of just Fg, we'll say F net. So some unbalanced non-zero force is going to be equal to the mass of the object the force is acting on times the acceleration that object is experiencing. So the size of the force is equal to the mass of the object times the acceleration of that object. It's very similar to the gravity formula we looked at yesterday. We're just generalizing it now to any acceleration, not just the acceleration due to gravity. When Newton originally threw this down, he didn't actually write it like this. This is the more useful way to represent it. He wrote it like this. He said that the acceleration is equal to the net force divided by the mass, because it's easier to measure the force on the object than it is to measure its acceleration. But these are equivalent. If you recall what a net force is, I'll write this down over here. F net is the sum of all forces in the direction of motion. So add them all up in the direction the object's moving in, and that'll be your net force. I'll do a bunch of examples of what this looks like. If we take a look at the units here, the units are interesting, and they start to get weird. When I first introduced to you guys the concept of force, what were the units that we gave it? Units of force are measured in? Sorry? Newtons. So a force is measured in newtons, named after the guy responsible for first giving us these concepts. But if you compare them, the Newton, force is measured in newtons, you compare that to values, or units rather, that we've got over here, you can see why we bring in the Newton. Mass is measured in what? kgs. And we're multiplying a mass by an acceleration. The units for acceleration are meter, not meters per second. That's a velocity. Acceleration is meters per second squared. So this is why we bring in something like the Newton. We simplify the units on the force. Say, oh yeah, forces are going to be measured in newtons. But a force is equal to a mass times an acceleration. So an equivalent set of units would be a kilogram meter per second squared, which is a lot more cumbersome to deal with. This relationship, though, both of these would be sets of units for force. So I'm going to do 5 examples of this, and then I'm going to let you play. All of these must include FBDS's. FBD stands for free body diagram. If you weren't here, I'll demonstrate for you again what a free body diagram looks like. For those of you who were and may have forgotten, a free body diagram is just the object and whatever forces are acting on the thing. So let's take a look. A 5 kilogram block is pushed to the right along a frictionless track with a force of 10 newtons. What is its acceleration? So let's draw the thing. Here's our object, a 5 kilogram block. I'm gonna grab another color. Here's the track. And now let's label all the forces. What forces are acting on this thing? Gravity. Gravity is always acting unless you're somewhere else. Straight down. What other forces are acting on this thing? Sorry? A normal force. Whenever you're sitting on a surface or in contact with a surface, you have a normal force that is perpendicular to the surface. So in this case, because the surface is left-right, Fn is up-down. So we've got an Fn and an Fg. What do we know about those two? They're equal because the block's not being flung up into the air. It's not being pulled down into the table. So these two have to be equal. And are there any other forces acting on this thing? What word in there suggests to you that there's an applied force? Pushed. Absolutely. That word pushed implies that there's an applied force, and we don't know what else to call it. We don't know what's doing the pushing, so yeah, call it Fa. To the right. Is that it? Brad?
It's a frictionless track, so doesn't that mean it's FA plus F because it's going on it?
If it's, does friction ever go with motion?
Oh, so is it just neutral?
It's just not there, yeah.
Oh.
Frictionless implies there is no friction. Friction will never help you move. It only ever impedes motion.
Oh, okay.
So frictionless track implies F force of friction is 0. That's what I was looking for, though. That language there suggests there's nothing else. You've got a normal force of gravity and an applied force there. And we're given some values. We know the value for the applied force. The applied force is 10 newtons. So we can include that in our diagram. But now we can actually go ahead and find values for these other things too. Yesterday, I gave you a formula for the force of gravity. The force of gravity is equal to the mass of the object times the gravitational field strength wherever that object is. And again, if it doesn't explicitly state, you're on Earth. So if Fg equals mg, and this is a 5 kilogram block, that means the force of gravity is going to be 5 times 9.8, which is 49 newtons. So you've got a 49 Newton force down acting on this block. And Ray, you said that the normal force, because there's no other forces up and down, these two must be equal. So you've got an Fn that's also 49 newtons. So now, more than just labeling the arrows, we can actually have to put values to these things. Got a 49 Newton gravity, a 49 Newton normal force, and a 10 Newton applied force to the right. And now we want to know what the acceleration of the block is. Now over here I wrote in blue, it might have been hard to see, and if it was, I'm sorry. F net is the sum of all the forces in the direction of motion, and we can use that to find the acceleration. So this is the formula that we're going to start with now. Everything we do in this unit, we don't have a bunch of formulas like we did in kinematics. It all starts here. So to find the acceleration of this block, we're going to start with F net equals ma every time. And F net is, again, the sum of the forces in the direction of motion. Which way is this block moving? Forward or to the right. So what forces are acting in that direction? Like, if it's moving left-right, I want all the forces that are acting left-right. This 10 Newton force is the only one. So when we're looking for the sum of the forces, there's only one. So in this one, it's going to just be that applied force is going to be equal to the mass times the acceleration. And now we can start to put in these values. We know that the applied force is 10 newtons. We know the mass of the object is 5 kilograms. And the acceleration is the thing that we're looking for. So what is going to be the acceleration here of the block? 10 divided by 5 is going to be 2. Let's give it the units, meters per second squared. And because acceleration is a vector, it also needs a direction. Which direction is this block going to be accelerating in? It's to the right. So that 10 Newton force is going to cause this block to accelerate at 2 meters per second squared to the right. And now if I wanted to, or if you guys wanted to, we could figure out what the velocity would be after a certain amount of time, or how far it would go, or everything that we did in the first chapter with kinematics is now fair game once we calculate this acceleration. Let's do a couple more examples. You've got a 650 kilogram car accelerating at 4 meters per second squared south. What is the net force acting on the car? So let's draw this thing from the top. We'll draw our free body diagram. There's our car. South is awkward. Again, we can assume it's down the page. So here's our wheels. Got a car driving down the page. What forces are acting on the car that we can draw, include in the diagram? Fn? Why? Just because I asked why doesn't mean you're wrong. Why is there a normal force? A typical car is going to be driving on the road. Anything that's in contact with a surface needs to have Fn. This is going to be an interesting diagram to draw Fn on, though, because we're doing a top view. So here's how you draw forces that are into and out of the page, because we want to include them. I'll put them up here. We're going to use this symbol, an X, for any force that is into the page. And we're going to use a dot for any force that is out of the page. Just because they're awkward to draw doesn't mean you don't have to include them. We have notation for everything. So a normal force, Raina, you're absolutely right. The cars typically drive on the road. So we need to include a normal force up out of the page. So we're going to put a dot right in the middle of the car, and we're going to call that thing Fn. What other forces do we need to? Yeah, gravity. Gravity is going to act, because this is a top view, gravity is acting down into the page. So right next to that Fn, because they technically should be on top of each other, but that's going to make things really messy if we do, we can put the X for a force into the page. And we'll call that thing Fg. The reason we use X's and dots is because we use arrows to represent these forces. Forces are vectors, they have a direction. And if you're looking at, if Alex decides to shoot an arrow at me from way over there, all I'm going to see coming at me is the point of the tip of the arrow as it flies towards my face. So that's why we use the tip. What Alex is going to see as the arrow leaves him is the feathers on the back, the notching. So that's why we use an X for something that's going away for us. X represents the back of the arrow. This represents the point of the arrow for anything that's coming into or out of the page. So we've got some values here. How do I find Fg? Sorry? G is going to be 9.8. Little g is 9.8. Yesterday we looked how the force of gravity is going to be equal to the mass of the object times the acceleration due to gravity. So what's the mass of the car in this question? It's going to be 650. So 650 kilograms times 9.8 is going to give you what force of gravity? Sorry? What did she say? It's going to be measured in newtons. I want the number, though. Someone grab a calculator. What's the number? What is the force of gravity acting on the car? 650 times 9.8 is not 49. It's going to be a lot bigger than that. (6,370 newtons. That is the size of the force of gravity acting on the car. And because the car is not being launched into the air or crushed into the ground, Fg and Fn are going to be equal and opposite. So the normal force is going to be what? Well, the value is going to be the same, 6,370. We haven't called a direction positive or negative. We just know it's going to be out of the page. Neither one should be any. You choose. Do you want into the page to be negative or out of the page to be negative? It's totally arbitrary. So because we've got these symbols here, we know one is into, we know Fn is out of the page. We know Fg is into the page. We don't actually need to say which one's positive and which one's negative at this point. We know one is in and one's out. One's out. We've got the direction there already. The only other thing to add is that we know that there's a net force acting on this car. Which way? Yeah, down the page, or in the question, it's south. We know there's a net force south because there's an acceleration south. Yeah. See, this is beautiful. I'm glad you asked the question. Yeah, but what's F net? The F net is the sum of all the forces. And so that's the easy way of getting away from saying, I don't want to deal with drag. Because you're right.
Regardless, it's going at that page. So.
Absolutely correct.
Okay, so if it's not.
So you're right. There's going to be friction in the wheels. There's going to be drag on the car. There's going to be acceleration from the engine. We're ignoring all of that by saying the car has a 4 meter per second squared acceleration. So even though those individual forces I might not be able to calculate, I know there has to be the sum of all of those forces is going to be south. And we can ignore all of the individual pieces by just saying, I know I'm looking for the net force, and I know there's an acceleration south. So the net force must then also be south. I'm so glad you asked the question, Brad. And so now we can go ahead and find it. We know that we know the formula for F net. F net is equal to the mass of the object times its acceleration, and we know the mass and the acceleration. So you're going to have 650 is your mass times 4, the acceleration of the car. So F net, I'll give you the value, I've got it here, 2,600 newtons south. So Brad, because you asked the question, if the net force is 2,600 newtons, what can you tell me about the applied force from the engine? How is the applied force from the engine going to relate to this number? This is the net force. So the acceleration is 4. We know that the net force on the car, the sum of the forces in the direction of motion, are producing this acceleration. So Brad, you asked before, what about drag? What about friction? Those things are going to impede, right? They're going to be acting backwards. The applied force is going to be dragging the thing forwards. So what can you tell me about the applied force from the engine as it relates to this value? Kai. Has to be bigger. So the applied force is going to be bigger than this value. So the engine's producing a larger force than this because the drag backwards, the friction backwards, is going to take away from the applied force to give us this value. That's how all of that relates together. Yeah. Yes.
All the things pulling it back are leading it to that?
Yes.
Oh, okay.
Yes. Which brings us to a concept that we can talk about called efficiency. Efficiency is what percentage of what you are actually doing is useful, which we won't bring into this chapter, but we'll bring in that idea, though, we're going to bring into subsequent chapters. We know the applied force is greater than this, but this is what's actually happening. And so now, for those of you who are interested in going into engineering, this is the kind of thing that you start to compare. How do I reduce the drag so that the applied force on the car is maximized? How can I design a car? How can I design a plane? How can I design a jet so that as much of the applied force as possible goes into actually pushing the car forward, and we reduce drag and we reduce friction and all that kind of thing. And then you get these extreme examples of vehicles like supercars and F1 and all of these kinds of things. Okay, a couple more examples and I'll let you play. A 1,500 kilogram ice cream truck accelerates from rest to a top speed of 45 kilometers per hour in 8 seconds. That is brutal. Yes, sir.
We don't want to use the X robot. We just draw 3D and have our own surface.
Technically, yes, but this isn't just notation I made up. This is standard for all time. You're going to see this notation in three-dimensional problems now forever. You are allowed to not like it, but you need to get used to it. You're not going to be able to, like some of the more complex stuff you're going to look at, you're not going to be able to draw in 3D. And there's no expectation that for those of you who struggle to draw in 3D, actually have to do it, because the notation exists. So for now, the answer is yeah, go for it. Draw me in these problems in 3D, but get used to the notation as well. Okay, so 1,500 kilogram ice cream truck accelerates from rest to a top speed of 45 kilometers per hour in 8 seconds. That's really slow. What is the net force acting on the truck? Okay, cool, let's draw the truck. There's the ice cream truck. It's a block on wheels. It's on the ground, because I don't know that ice cream trucks operate anywhere else. So the forces that we can draw are Fg, because it's on Earth. There's nobody wanting ice cream anywhere else. It's on the ground, so Fn is straight up. And if the truck is accelerating, I placed it on the left-hand side of the page, so the only way this thing can go is this way. And we'll call this the net force. We know it's accelerating to the right, so let's call that the net force acting to the right. We can find some values here. Fg is mass times gravity. So I'm not going to write it out now fully every time. I'm just going to start pulling out my calculator and doing it. The mass is 1,500. Gravitational field strength is 9.8, which gives us the force of gravity on the truck to be 14,700 newtons. The normal force is going to be equal to and opposite that, because it's in the opposite direction. And now I want to find the net force. Well, net force is going to be equal to the mass of the truck times the acceleration of the truck. So that's going to be 1,500 times the acceleration of the truck. What's the acceleration of the truck? No, that's the top speed of the truck. So that 45 kilometers per hour, that's the final velocity of the truck. What was the initial velocity of the truck? The initial velocity of the truck was 0. How long did the truck accelerate for? 8 seconds. That's what we want to find A. This is a kinematics problem. We've done the chapter already, so now I can start to give you concepts from that chapter that you now have to pull forward into this chapter. Everything builds. So what kinematic equation am I going to use to find the acceleration? Vf equals Vi plus At. Cool. So I've got what I know, I got what I'm looking for, I now have a kinematic equation that relates those things together. Before I plug anything in, what do I have to do first? I got to convert something. What are you converting? The which? We could, well, if you converted the, Yeah. If you put the time into hours, you're going to get an acceleration in kilometers per hour squared, and that's going to be terrible every time. So you want to make sure you put these, you want accelerations in meters per second squared. So we're going to convert the velocity. How do I convert kilometers per hour into meters per second? Divide it by 3.6. So what's the final velocity of the ice cream truck in meters per second? That was a quick test. Nice. What's 45 divided by 3.6? 12.5. You bet. So now we can go ahead and we can plug in those values. We can find out what the acceleration is, and then we can use that to figure out what the force on the truck has to be. So VF is 12.5. VI is 0. Plus A, what we're looking for, times 8 is the time. So what's A? 1.56 meters per second squared. So I can take this value and plug it in over here. 1.56. And we can find that the net force on the truck has to be what value? You've got a heavy truck accelerating slowly. What's the force have to be, Brad? Think about what that would mean, though. 45 times 3.6 is 162, and that would be meters per second. That means you're moving a football field and a half every second. Is that a reasonable speed for an ice cream truck? No. That is the most terrifying ice cream truck I think I've ever experienced. And that's an easy way to determine whether or not you're going the right way. Is an ice cream truck going to move a football field and a half every second? There's only one ice cream truck I can think of that would do that. And that's from a PlayStation game called Twisted Metal that came out for the PlayStation 2 back when I was in elementary school. So it's got to be the other one. Emma, can you give me the rest of this value? 22,932. And that's going to be in newtons. So there's a massive force, 22,000, almost 23,000 newtons. That is a large force, even though the acceleration is small. Oh, is that wrong? There should be a decimal place in there somewhere. 2,240. 1,500 times 1.56. I also got 2,340. 2,340. Okay, so 1,500. That's still a large, not nearly as large as it was before. 2,340 newtons. It's a heavy truck. It needs a lot of force to move it. Okay. Thank you for the correction. 2 more. Stan and Kyle. We're going to leave these 2 boxes here empty. We're just going to go to the examples. Stan and Kyle are pushing a 75-kilogram sled along frictionless ice. Stan pushes 55 newtons. Kyle pushes 45 newtons. We want to find the acceleration of the sled. So let's draw it. When in doubt, for those of you who are not artistically inclined, boxes work great. There's the sled. You want to make it look more sled-like, we can put runners on it. There's the sled. Here's the frictionless ice rink. Let's draw the free body diagram. What forces are acting on this thing? Gravity. And we can figure out the value right away. We know the mass of the sled is 75. So what is the value for the force of gravity? $735. Kai, you get the same thing? Which means Fn, which is all because the sled is on the ground, Fn also has to be 735. Thank you, Kale. What other forces are acting on the sled? Fa, where? An applied force from? From what pushing? From Stan and Kyle. So rather than, you're right, those are applied forces, but we can get more specific than just calling them applied forces. We can literally call them the force from Stan and the force from Kyle. When specific names exist, we can use them. So because I've placed this object on the left side of my page, let's assume that they're pushing to the right. Yeah?
Would you expect us to use them?
If you called them FAs, two different applied forces, you just have to call them different applied forces. You call one F a force applied 1 and force applied 2. If you're going to use the same name for the forces, you have to differentiate them somehow because they are different. So sure, if we did this, we could say, okay, well, I've got FA1, and now we've got a second push to the right. We could call it FA2. There's no reason why we couldn't use the language of applied force. But if they give you names in the problem, we can use those too. We could call the force applied 1 F Stan, and we could call force applied 2 F Kyle. I'm not going to be picky about how you choose to label them, but you need to differentiate them from each other. You can't call them both applied forces unless you call them applied force 1 and 2, for example. And we're given values for that. Stan is stronger, so he's apparently pushing at 55 newtons. Kyle is weaker, so he is pushing at 45 newtons. And that's our free body diagram. So now we want to find the acceleration of the sled. Everything we do in this chapter starts here. F net equals ma. So what are the forces acting in the direction of motion in this problem? One second, Brad. The 735 came as force of gravity is mass times the mass of the object times the field of gravity.
Oh.
So this came from 75 times 9.8. Iram, you have a visitor. Okay, so yeah, Emma, you were saying something. Answer my question first. It'll make your question easier. My question was, what are the forces acting in the direction of motion? Which way is the sled going to go? To the right. So what forces are acting left, right? According to my diagram. Henry, I haven't heard from that back table in a while. Oh, I'm not asking you to answer. I want an answer from your table. Discuss as a table and give me an answer. What forces are acting in the direction of motion? Yeah, Stan and Kyle. All we're doing is literally looking at the thing. Which ones are acting left, right? Stan and Kyle. Those arrows are pointed to the right. F net is the sum of the forces in the direction of motion, the thing's moving to the right. So F net is going to be the force from Stan plus the force from Kyle. And that's going to equal the mass times the acceleration. And, and now I can start to put values in. What is F Stan? How big is it? 55. How big is F Kyle? 45. What's the mass of the thing accelerating? Sorry? 75. It's a 75 kilogram sled. Times A. We're looking for the acceleration of the sled. And so now we've got something easy we can solve. 55 plus 45 is 100. That's going to equal 75A. What's A? So what I'm hearing you say is 1.3 repeated. So I'm going to put the little line above the thing. Meters per second squared. Acceleration of the sled, assuming Kyle and Stan continue pushing the way they're pushing, is going to be 1.3 repeating meters per second squared. Good. Let's do one more. Questions, comments, concerns about what happened here first? Okay. Last one. The Batmobile. Cool. We've got an object now worth drawing. So here's my artistic skills. This is what my son's Hot Wheels Batmobile looks like. You've got the fin, and it's got the spikes on the back, and it's got the little jet engine there, and it goes, and it comes to a pointy face. It looks like a fighter jet on wheels. You know, the Batmobile, totally unnecessarily, always has flames coming out of the back. Wildly unnecessary, but that's okay. They're cool. There's the Batmobile. Let's keep reading the problem. Batmobile exerts a force of 8.5 times 10 to the 3 newtons east, while friction pulls back on it with a force of 1,500. So Brad, this is your question from a second ago. We've got this force being exerted. That's the applied force from the jet engine. This is the friction or drag or whatever pulling back at 1,500. If it has a mass of 1,250, what's the acceleration of the Batmobile? So, now we bring everything into consideration. Let's draw the free body diagram. What are the forces acting on the Batmobile? Gravity. The quicker someone says gravity, the quicker they don't have to give me any other answers, and gravity's always there. To find the force of gravity on the Batmobile, we take its mass and we multiply it by 9.8. What's the force of gravity on the Batmobile? Someone give me the value. $12,250 kilograms. Newtons. Oh, newtons. You don't know? Okay. Yeah. No, I put the wrong units down. You're good. That's Kaylin, you got that value too? Because I saw you punching into your calculator. Yeah, same value. And because this thing's acting on the ground, which is not something you can assume always of the Batmobile, the normal force is going to be the same. 12,250 newtons. And now we've got an applied force forward from the jet engine. And if we're told that there's a friction force, which way is it going to act? To the left. So it's included in the diagram. Force of friction back. The applied force has a value. 8. Well, it's given to us in scientific notation. If you don't like scientific notation, you just punch this into your calculator. What's 8.5 times 10 to the 3? So that's something that should be relatively easy to do in your head. You just take the decimal and you move it this many times to the right. So instead of 8.50, it's going to be 8,500 because we move the decimal 3 places to the right. 1, 2, 3. We put a 0 there. We've got an 8,500 Newton force to the right, and friction's acting opposite of motion, and we're told it's 1,500 newtons. So there's all the forces acting with all of their values. Cool. Now we can go ahead and figure out what the acceleration is. Everything starts here. F net equals ma. This is the first one. First, and well, it's the last example, but it's the first example where we've had forces acting in opposite directions along the motion. So what's that going to look like for F net? Only what's labeled. They said friction. Well, the question uses the concept of friction, but I mean, that's going to be air resistance too. It all gets lumped into that idea of friction. These two forces are acting in opposite directions. So when we put them into the equation, one of them is going to have to be positive, while the other one's going to have to be negative. They're acting in different directions, and that's how we determine which one's that's how we differentiate them. One's got to be positive, one's got to be negative. So which way do you want to call positive? Now it matters. You want to call east positive or keep the big one positive? Makes a lot of sense. So so put that on your free body diagram as well. If we're going to call one of the directions positive, label it. So if to the right is positive, now all of a sudden your F net is going to become the applied force minus your force of friction. These two are acting along the direction of motion. This direction you called positive, this direction is negative. So it's going to be applied force minus friction equals ma. And now I can start to put all these things in here. The applied force was 8,500 minus 1,500 equals the mass of the Batmobile, 1,250 times A. What's the acceleration of the Batmobile? Sorry? 5.6 meters per second squared. And just to pull it all together, the very first thing we talked about today was the idea of G-forces. How many G's is the Batman experiencing right now? 0.57 G's. You divide that by 9.8, and you're going to find the Batman is experiencing 0.57 G's. Which, if you think about the last time you watched a Batman movie and how his face is all like, as he's accelerating, it shouldn't be, because 0.57 G's is nothing. He should be confidently cruising as the jet forces his car forward at 5.6 meters per second squared. That's it. We're done. Comments, questions, concerns about anything we've done? Cool. Then y'all got to practice this stuff. Here's what I'd like you to do. I want you to start. I want you to start here. This page, all of it. The first question, the first 6 are for each of the following diagrams. All you need to do is determine the magnitude and the direction of the net force. That's what you do for the first one. For the second one, I want you got to fill in all the missing blanks. So what forces are missing? And I want the accelerations for all of these blocks. And because I haven't given you an abundance of time, that's all I'm going to do today. Tomorrow we'll go ahead and take a look at these questions here, but you don't need to worry about those today. I just want you to get this page done. This is your home, well, and you should get a bunch of those done over the next 9 minutes. This is what I want you to look at on your Market Say Giver.